Every summer in one of the world's major oceans, a zone the size of the state of New Jersey appears where there is almost no fish. Not because they were caught, but because there is nothing to breathe. The oxygen in the water drops to a level at which nothing larger than a bacterium can survive. Crabs flee to shore. Fish run or die. The bottom is covered in dead organic matter. This is called a dead zone. And today there are more than 500 of them across the world's oceans. But here is what almost nobody talks about. The exact same process, the same chemistry, the same mechanism, the same end result has already played out on a global scale several times in the history of Earth. And every single time, it ended the same way: mass extinction. Before we continue, please subscribe to this channel. Your support makes this work possible, and there is much more to explore. Thank you. Let us start with what a dead zone actually is, because the name is evocative, but the reality is more specific and more disturbing than the name suggests. A dead zone is a region of water so depleted of dissolved oxygen that most marine animal life cannot survive in it. The technical term is hypoxia, from the Greek for under and oxygen, and the threshold for marine hypoxia is typically defined as dissolved oxygen concentrations below 2 milligrams per liter. For context, well-oxygenated surface seawater typically contains 7 to 8 milligrams of dissolved oxygen per liter. Below 2 milligrams, the physiological stress on fish, crustaceans, and most other marine animals becomes acute. Below 1 milligram, the threshold for severe hypoxia, almost all multicellular marine life either flees or dies. And in the most extreme cases, the oxygen drops to essentially zero, a condition called anoxia. In anoxic water, even bacteria that require oxygen are absent. Only anaerobic bacteria, organisms that do not need oxygen and that are in many cases poisoned by it, can survive. The mechanism by which dead zones form is straightforward once you understand it, and it involves a chain of events that begins not in the ocean, but on land. In the modern context, the chain typically begins with agriculture. Fertilizers applied to farmland, fertilizers rich in nitrogen and phosphorus, are carried by rain into streams and rivers, which carry them to the coast. In the coastal ocean, this excess nitrogen and phosphorus acts as a fertilizer for phytoplankton, the microscopic photosynthetic organisms that form the base of the marine food web. The phytoplankton bloom dramatically, sometimes turning the water vivid green, red, or brown, sometimes producing toxins that contaminate shellfish. Then the bloom collapses. The phytoplankton die and sink. Their decomposition is carried out by bacteria, and bacterial decomposition consumes oxygen. In a thick, dense rain of dead phytoplankton settling toward the bottom, the bacterial decomposition is so intense that it consumes all available oxygen in the deeper water faster than it can be replenished from above. The replenishment of deep water oxygen depends on vertical mixing, the physical movement of surface water downward and deep water upward, that brings oxygenated surface water into contact with the oxygen-depleted depths. This mixing is driven by wind, by temperature differences, and by density differences between water layers. But when the surface water is significantly warmer than the deep water, which happens in summer when solar heating warms the surface layer, the density difference between the warm light surface water and the cold dense deep water inhibits vertical mixing. The warm surface layer floats on the cold deep layer like oil on water, and the exchange between them is severely reduced. The stratification of the water column traps the oxygen-depleted deep water in place, cut off from the surface. This combination, nutrient-driven biological productivity, the rain of dead organic matter to the bottom, and thermal stratification that prevents reoxygenation, is the recipe for a dead zone. It is not complicated. It is not mysterious. It is straightforward physics and chemistry operating according to well-understood principles. And it is creating regions of the ocean that are fundamentally uninhabitable to most marine life, growing in both number and extent. In one of the most biologically productive periods in human history, the period during which industrial agriculture has flooded coastal waters with nitrogen and phosphorus on an unprecedented scale. The numbers are striking, and they are getting worse. In the early 1960s, oceanographers had documented fewer than 50 hypoxic zones in the world's coastal waters. By 2000, there were more than 400. Today, the count exceeds 500, and some researchers believe the true number is higher because monitoring coverage in many parts of the world remains inadequate. The largest dead zone in the Western Hemisphere appears reliably every summer in the same coastal waters, fed by the nitrogen runoff from the agricultural heartland of North America, carried by river to the coast. At its peak in recent years, it has covered areas between 6,000 and 9,000 square miles, comparable to the state of New Jersey. It is not a permanent feature of the geography, but it is reliably seasonal, returning year after year with a consistency that has the character of something chronic rather than something accidental. The Baltic Sea is in many ways an even more extreme case. The Baltic is a semi-enclosed sea with limited exchange with the open North Atlantic. Its basin is deep, its stratification is strong, and its catchment area encompasses some of the most intensively farmed land in Europe. The Baltic has been experiencing hypoxia in its deep basins for centuries. There is evidence of pre-industrial hypoxia from sediment cores, but the scale and intensity of the modern hypoxia is dramatically larger than any natural baseline. The anoxic zone in the Baltic today covers an area of approximately 27,000 square miles and reaches depths of nearly 400 feet. The sea floor of these anoxic regions is populated almost exclusively by mats of sulfur bacteria, organisms that use hydrogen sulfide rather than oxygen as their energy source, producing the rotten egg smell characteristic of severely oxygen-depleted water. The sediment in the anoxic Baltic basin is black, not the grey-brown of normal marine sediment, but jet black. Because the absence of oxygen allows the accumulation of iron sulfides rather than the iron oxides that color oxygenated sediment. The black sediment is a color-coded record of anoxia, readable in core samples as a physical signature of the death of the bottom ecosystem. The Black Sea offers perhaps the most extreme modern example of what a permanently anoxic body of water looks like. The Black Sea is stratified into two fundamentally different bodies of water: an upper layer of relatively oxygenated brackish water, fed by the freshwater input of the Danube, Dnieper, and Don rivers, and a lower layer of dense, salty, completely anoxic water that constitutes approximately 90% of the total volume of the sea. The boundary between these two layers, the chemocline, is at roughly 600 feet depth. Below 600 feet, there is no dissolved oxygen anywhere in the Black Sea. The deepest water is not merely low in oxygen, it is not merely hypoxic, it is lethally, permanently anoxic, saturated with hydrogen sulfide, produced by the anaerobic bacteria that are the only organisms capable of living in it. The Black Sea is below 600 feet, a dead sea in the literal sense, an enormous volume of water in which no complex life can exist. This is the modern face of ocean deoxygenation. 500 dead zones. A dying Baltic, the Black Sea as a vast natural anoxia experiment. But here is where the story takes its first major turn, because this is not a new story. It is, in fact, a very old one. The geological record of the oceans contains multiple episodes of what scientists call Oceanic Anoxic Events, OAS. Periods during which large portions of the world ocean lost their oxygen, sometimes to depths well below the surface, sometimes across entire ocean basins. These events are recorded in the sediment as distinctive black layers, organic rich black shales and mudstones that are chemically and physically distinct from the normal grey-brown sediment deposited in oxygenated conditions. The black color comes from the same iron sulfide chemistry visible in the modern Baltic anoxic sediment, amplified by the much higher organic carbon content that accumulates when decomposition is inhibited by the absence of oxygen. The most intensively studied oceanic anoxic event is OAE2, which occurred approximately 93 to 94 million years ago during the late Cretaceous period, a time when dinosaurs roamed the land and the ocean was warm and globally more connected than today. OAE2 was not a local or regional event. It was global. The black shale layer that marks OAE2 can be found in rock exposures on every continent, in ocean sediment cores from every major ocean basin, in rocks that were deposited in shallow coastal seas and in deep open ocean environments. The event lasted approximately 600,000 years. Brief by geological standards, but approximately twice as long as our species has existed. And during this interval, the oxygen concentration in the deep ocean dropped precipitously across most of the world. What caused OAE2? The mechanism involved the same basic elements as modern dead zones, but operating at planetary scale and triggered by geological rather than agricultural forces. A series of major volcanic events, the eruption of the Caribbean Large Igneous Province being the leading candidate, injected enormous quantities of carbon dioxide into the atmosphere over timescales of hundreds of thousands of years. The increased atmospheric carbon dioxide drove global warming. Global warming reduced the solubility of oxygen in seawater. Warm water holds less dissolved gas than cold water, just as a warm soda goes flat faster than a cold one. Simultaneously, the warming reduced the temperature difference between high and low latitudes, weakening the atmospheric and oceanic circulation that normally drives the downwelling of cold, dense, oxygenated water from the poles to the deep ocean. The deep ocean, deprived of its normal oxygen supply from polar downwelling, became progressively depleted. When the deep water became anoxic, the decomposition of organic matter at depth was inhibited, allowing enormous quantities of organic carbon to accumulate in the sediment. The organic-rich black shales that now mark OAE2 in the rock record. The biological consequences of OAE2 were severe. Multiple groups of marine organisms showed significant diversity loss during the event. Certain group of foraminifera, the microscopic shell-forming organisms whose remains dominate deep-sea sediment, showed dramatic reductions in diversity or local extinction during the anoxic interval. Larger marine animals were similarly stressed. The OAE2 boundary in many rock sections is marked by a distinct change in fossil assemblages. Species present below the boundary absent above it, replaced by a simplified community better adapted to low oxygen conditions. But OAE2 was not the most extreme of the oceanic anoxic events, and it was not the most biologically consequential. That distinction belongs to the series of anoxic events associated with the end-Permian extinction, approximately 252 million years ago, the largest mass extinction in Earth's history, the event that eliminated approximately 96% of all marine species and 70% of terrestrial species. The end-Permian event has multiple contributing causes: the Siberian Traps volcanic eruptions, ocean acidification, global warming. But ocean deoxygenation was a critical and possibly the primary driver of the marine extinctions. The chemical evidence from end-Permian marine sediments points to a catastrophic expansion of anoxic conditions in the ocean that would have made large portions of the marine realm uninhabitable for any organism requiring oxygen. The mechanism was essentially an extreme version of what we see in modern dead zones, amplified to planetary scale by the volcanic forcing of the Siberian Traps. The volcanoes warmed the climate. The warming reduced oxygen solubility. The warming reduced polar circulation. The deep ocean lost its oxygen supply. The deep sea became anoxic. The anoxia expanded into shallower water. The oxygen minimum zones, the natural low oxygen regions that exist in all modern oceans at depths between 300 and 3,000 feet, expanded dramatically, squeezed the available habitat for marine life from below, while the warm acidified surface water squeezed from above. The surviving species were those that could tolerate low oxygen, high temperatures, and high acidity. Most could not. Here is the thing that should make you stop and think. The mechanism operating in modern dead zones, warmer water, reduced oxygen solubility, weaker circulation, expanding oxygen minimum zones, is the same mechanism, scaled down, that drove the end-Permian marine extinctions. The same chemistry, the same physics, the same cascade of consequences. The difference is one of scale and rate, not of kind. The end-Permian warming happened over tens of thousands of years, driven by the Siberian traps releasing carbon dioxide on timescales that now look, compared to industrial emissions, almost gradual. The modern warming is happening on timescales measured in decades. The chemistry does not know the difference between volcanic and industrial carbon dioxide. It responds to the concentration, not the source. This is where the parallel between ancient and modern becomes genuinely uncomfortable. The global ocean has lost approximately 2% of its dissolved oxygen over the last 50 years. 2% sounds small, but 2% of a very large number is still a large number, and the distribution of this loss is not uniform. The oxygen minimum zones, those natural low oxygen layers that exist at intermediate depths in all major ocean basins, have expanded significantly. In the Eastern Pacific, the oxygen minimum zone has expanded both laterally and vertically, pushing into shallower water where fish and other organisms previously had refuge from the low oxygen conditions below. In the Atlantic, measurement campaigns over the last several decades have documented oxygen losses in the deep water that exceed what would be expected from warming alone, suggesting that circulation changes are also contributing to the deoxygenation. The term oxygen minimum zone deserves explanation because it is central to understanding what is at stake. In every major ocean basin, there is a layer at intermediate depth, typically between about 300 and 3,000 feet, where the oxygen concentration is naturally at its lowest. This layer forms because it is below the sunlit surface zone where photosynthesis produces oxygen, but above the cold deep ocean where oxygen-rich water sinks from polar regions. In this intermediate zone, the oxygen that sinks from above is consumed by the respiration of organisms living there, and by the bacterial decomposition of organic matter raining down from the productive surface. The oxygen consumption rate exceeds the supply rate, creating a natural oxygen minimum. In some parts of the ocean, particularly in the eastern tropical Pacific, the northern Indian Ocean, and the Arabian Sea, these oxygen minimum zones are naturally very intense, with dissolved oxygen concentrations below 1 milligram per liter in their cores. As the ocean warms and circulation slows, these oxygen minimum zones expand. The boundary of the oxygen minimum zone moves upward into shallower water, reducing the habitable depth range for fish and other oxygen-dependent organisms. It also moves laterally, expanding the geographic area covered by low oxygen conditions. Fish, squid, and other mobile organisms can potentially track the shifting oxygen boundaries, but the fish's prey, often less mobile, cannot always escape as quickly. The restructuring of the three-dimensional oxygen landscape of the ocean has cascading effects on food webs that are not simple to predict or model. The specific consequences for economically important fish species are already becoming visible. Many commercially important fish, tuna, billfish, mahi-mahi, and numerous others, are oxygen-sensitive animals with high metabolic rates that require relatively well-oxygenated water. As oxygen minimum zones expand, the vertical extent of the water column that these fish can occupy is compressed. They become concentrated in a shallower and shallower surface layer, which makes them more catchable, a perverse economic benefit that masks the underlying ecological problem, but also exposes them to greater thermal stress and other surface layer challenges. The compression of available habitat by expanding oxygen minimum zones from below, combined with warming surface temperatures from above, represents what oceanographers call a squeeze. And the organisms being squeezed are the ones on which both marine ecosystems and human food security depend. The coastal dead zones are, in this framework, the most visible and locally immediate manifestation of a broader planetary-scale deoxygenation trend. They are the headline, but the oxygen minimum zone expansion is the story. And the story connects directly to the two great drivers of our current environmental predicament: the discharge of excess nutrients into coastal waters from industrial agriculture, and the warming of the global ocean from the accumulation of greenhouse gases in the atmosphere. These two drivers operate through different mechanisms, but produce converging effects. The nutrient discharge drives coastal eutrophication, the biological overproduction and subsequent decomposition that consumes oxygen in the near-shore environment. The warming operates through multiple pathways. It directly reduces oxygen solubility. It reduces the density difference that drives deep water formation and ventilation. It strengthens the stratification that traps oxygen-depleted water at depth. And it accelerates the metabolic rates of marine organisms, increasing their oxygen demand even as supply decreases. The combination of these two drivers is producing a marine oxygen crisis that is coastal in its most visible expressions, but oceanic in its deeper dimensions. The Bay of Bengal offers a striking case study. The northern Bay of Bengal has an extensive, naturally occurring oxygen minimum zone, fed by the high biological productivity of its surface waters, which are nourished by the nutrient-rich discharge of major rivers, including the Ganges, Brahmaputra, and Irrawaddy. Superimposed on this natural low-oxygen environment is additional oxygen stress from warming. The Bay of Bengal has warmed significantly in recent decades, and from increased nutrient discharge as the agricultural systems of South Asia have intensified. The oxygen minimum zone in the Bay of Bengal is one of the most intense in the world, with oxygen concentrations near zero in its core, and it has expanded measurably in recent decades. The Bay of Bengal supports some of the most productive fisheries in the world and provides protein for hundreds of millions of people in some of the world's most food-insecure nations. The compression of habitable space for fish in this ocean by an expanding oxygen minimum zone is not an abstract ecological concern. It is a food security issue of immediate human consequence. The west coast of North America presents a different and in some ways more alarming picture. The California Current System, the upwelling system off the coasts of California, Oregon, and Washington that brings cold, nutrient-rich water to the surface and supports some of the most productive fishing grounds in the Pacific, has been experiencing oxygen stress that goes beyond anything in the historical record. The upwelled water that rises to the surface along the Pacific coast of North America originates in the oxygen minimum zone of the North Pacific, where it has been accumulating carbon dioxide and losing oxygen for decades as the ocean has warmed and circulation has slowed. The oxygen content of the upwelled water reaching the California coast has declined measurably since the 1980s, and in some years, The water reaching the seafloor in the near-shore environment is severely hypoxic or anoxic, producing mass mortality events of crabs, fish, and other seafloor organisms on a scale that had not been previously observed in the historical record. These Pacific Coast hypoxia events attracted significant attention when they first became pronounced in the early 2000s, because they represented a genuinely new phenomenon in a region where such events had not been documented before. They are not driven primarily by nutrient pollution. The Pacific Coast upwelling system is not an agricultural runoff system in the way the Gulf system is. They are driven by the intrusion of already oxygen-depleted water from the expanding Pacific Oxygen Minimum Zone, combined with local warming that reduces oxygen solubility and strengthens stratification. They represent the open ocean oxygen crisis invading the coastal zone rather than the reverse. In this sense, they are a harbinger, a preview of what open ocean deoxygenation looks like when it interacts with the coastal environment. And here is where the geological parallel becomes most pointed. In the geological record of the Oceanic Anoxic Events, the expansion of oxygen minimum zones from the open ocean into shallow coastal and continental shelf environments is precisely what drove the most severe marine extinctions. The deep water anoxia that established itself during OAE2 and the end-Permian event eventually expanded upward and laterally, invading environments that had previously been oxygenated and eliminating the organisms that lived there. The modern oxygen minimum zone expansion on the Pacific coast of North America is a small-scale, early-stage version of this process. The ocean's deep oxygen-depleted layer extending its reach into waters that had not previously been affected. The rate of change is one of the most alarming aspects of the current situation. The geological Oceanic Anoxic Events developed over timescales of tens of thousands to hundreds of thousands of years. The current ocean deoxygenation has developed measurably over 50 years, approximately 1,000 times faster than the geological events. The ocean has not had time to adapt biologically. Species cannot evolve new physiological tolerances in 50 years. Ecosystems cannot restructure themselves to accommodate a fundamentally changed oxygen landscape in the span of human careers. The rate of change is faster than biological adaptation can track, which means the biological response will be displacement and mortality rather than adaptation, as it is in modern dead zones where the fish and crabs simply leave rather than adapting to breathe in low oxygen water. There is a specific and underappreciated aspect of ocean deoxygenation that receives almost no attention in public discussions of ocean health: its interaction with the nitrogen cycle. Dissolved oxygen in seawater is not merely a resource for fish to breathe. It is a key participant in the ocean's biogeochemical cycles, including the nitrogen cycle. In oxygenated water, nitrogen exists primarily as nitrate, the oxidized form that is a key nutrient for phytoplankton. In anoxic water, bacteria use nitrate as an alternative electron acceptor in the absence of oxygen, reducing nitrate to nitrous oxide or nitrogen gas. in a process called denitrification. The conversion of nitrate to nitrogen gas removes nitrogen from the biologically available pool. It is literally lost to the atmosphere as an unreactive gas. This might sound like it would reduce eutrophication, but the relationship is more complex because the intermediate product of denitrification, nitrous oxide, is a potent greenhouse gas, approximately 300 times more powerful than carbon dioxide on a per-molecule warming basis. Expanding oxygen minimum zones, therefore, increase the production and emission of nitrous oxide from the ocean, adding a direct climate feedback to the already complex cascade of consequences. The ocean's nitrogen cycle also interacts with oxygen through the process of nitrogen fixation, the conversion of atmospheric nitrogen to biologically usable forms. Certain cyanobacteria perform this conversion, and their activity tends to increase in low nitrogen, low oxygen environments, precisely the conditions that expand as oxygen minimum zones grow. The increased nitrogen fixation partially compensates for the nitrogen lost through denitrification. But the balance between these two processes is sensitive to oxygen conditions in ways that are not yet fully understood. And the net effect of expanding anoxia on the ocean's nitrogen budget introduces uncertainties into projections of future ocean productivity that are difficult to resolve. What do we actually do about this? The answer depends entirely on which part of the problem you are addressing. Because the coastal dead zone problem and the open ocean deoxygenation problem have different primary drivers and require different responses, though they share the common thread of the warming climate. The coastal dead zone problem is primarily an agricultural runoff problem, and in principle it has tractable solutions. Reducing the application of nitrogen and phosphorus fertilizers beyond what crops actually need, precision agriculture, would reduce nutrient loading to coastal waters. Restoring the wetlands and riparian buffers that naturally filter nutrients from agricultural runoff before they reach rivers would reduce the nutrient load reaching the coast. Redesigning agricultural drainage systems to retain nutrients in the landscape rather than flushing them to the coast would reduce hypoxia. These are not technically mysterious solutions. They are known. They are in many cases economically viable. The obstacle is not knowledge or technology. It is the political economy of agricultural subsidies and the diffuse, distributed nature of nutrient pollution, which makes regulation difficult and enforcement challenging. Some dead zones have recovered when nutrient inputs were reduced. The Black Sea dead zone in the northwestern shelf improved significantly in the 1990s, when the collapse of the Soviet agricultural system dramatically reduced fertilizer use in the catchment area. The improvement was temporary. As agricultural production recovered, nutrient loading increased again. But it demonstrated that the system can respond on timescales of years to decades when drivers are reduced. The Chesapeake Bay, which has been the subject of sustained restoration efforts for several decades, has shown measurable improvement in some oxygen metrics, though progress has been slow and incomplete. The system is recoverable. The question is whether the political will to recover it exists. The open ocean deoxygenation problem is fundamentally a climate problem, and its solution is the solution to climate change. the reduction of greenhouse gas emissions to prevent continued ocean warming. There is no targeted intervention that can reoxygenate the deep ocean without addressing the warming that is driving its deoxygenation. This makes the open ocean problem harder, both in the political sense that climate mitigation requires global coordination rather than regional agricultural policy, and in the scientific sense that the ocean's thermal inertia means that even if emissions were dramatically reduced tomorrow, the ocean would continue to warm and deoxygenate for decades to centuries, as the heat already absorbed by the surface ocean penetrated to depth. This is what oceanographers call committed change, the deoxygenation that is already locked in by the warming already experienced, independent of future emissions. The scale of committed change is not yet fully characterized, but the physics are clear. The ocean will continue to warm for decades after any given moment of emissions stabilization. And as it warms, the oxygen minimum zones will continue to expand. The question of how much committed change is already locked in, how much additional deoxygenation will occur regardless of what we do now, is one of the most important and least discussed questions in ocean science. Now let me offer the perspective that I think this evidence demands. Because the facts alone do not speak, they require interpretation. And I believe this particular set of facts has been systematically underinterpreted in public discourse. The framing of ocean dead zones as an environmental problem is accurate but insufficient. An environmental problem suggests something that is unfortunate, that represents a failure of stewardship, that would ideally be fixed, but whose consequences are primarily ecological. Dead zones kill fish. They destroy crab fisheries. They damage coastal economies. These are real harms, and they deserve serious attention. But the geological record frames this differently. The geological record says, here is a mechanism that, when it operated at planetary scale in the past, reliably produced mass extinctions. Not environmental degradation, mass extinction. The mechanism operating today in more than 500 coastal zones and at ocean basin scale in the expanding oxygen minimum zones of every major ocean is the same mechanism, the same chemistry, the same cascade, the same feedback loops. We are running the beginning of a process whose end state, when it has occurred in the past, was catastrophic by any meaningful definition. The rate at which we are running it is faster than the geological examples. The geological examples, OAE2, the end-Permian, played out over timescales that allowed some biological adaptation, some evolutionary response, some restructuring of ecosystems as conditions changed. We are running the same process at a rate that allows none of these responses. The organisms in the dead zones of today are the same organisms that lived in those waters when the water was oxygenated. They have not evolved new tolerances. They have not found new strategies. They are simply dying or fleeing. I am not arguing that we are necessarily heading for an end-Permian scale extinction event. The modern situation differs from the geological examples in important ways. The geographic structure of the ocean is different. The existing biological diversity is different. And we have the knowledge and, in principle, the capability to intervene in ways that no geological forcing event can. But I am arguing that the comfortable framing of dead zones as a manageable environmental problem that responsible stewardship can address adequately is not supported by what the geological record tells us about what happens when ocean deoxygenation reaches sufficient scale. The geological record tells us that ocean deoxygenation is one of the most effective and reliable mechanisms for catastrophic marine biodiversity loss that exists in Earth's history. It tells us that the process is self-reinforcing through multiple feedback loops. It tells us that the warning signs, the expanding oxygen minimum zones, the proliferating coastal dead zones, the measurable global oxygen decline, are exactly what you would expect to see at the early stages of a process that has gone much further in the geological past. And it tells us that the rate at which we are driving this process is without geological precedent. What I conclude from this is not despair. Despair is a response to problems that have no solutions. This problem has solutions, known solutions, technically feasible solutions, solutions that would require political will and economic restructuring, but not technological miracles. The agricultural nitrogen problem is solvable. The climate warming that is driving open ocean deoxygenation is a problem we understand and have the technical capacity to address. What I conclude is urgency. Urgency of a different character than the urgency typically applied to environmental problems. Not the urgency of protecting a scenic coastline or preserving a charismatic species. The urgency of recognizing that we are running a process that has, in the geological record, a very clear and very bad track record. The urgency of understanding that the 500 dead zones of today are not the end point of this process. They are the beginning of something whose geological analogues are among the worst events in the history of life on Earth. The ocean has been in crisis before. It survived those crises, though the life within it was largely replaced. We are the first species capable of reading the geological record of those crises and understanding what they mean. We are also, as far as we know, the first species capable of preventing a recurrence rather than simply enduring it. Whether we will use that capability is the most important environmental question of our time. The dead zones are the answer the ocean is already providing. Every summer, in more than 500 places, in water that once had fish. The chemistry does not care about our timelines. The oxygen minimum zones do not pause while we decide what to prioritize. The geological record does not offer comfort. It offers precedent. And the precedent is unambiguous about what happens when we let this process run. What we do with that knowledge is, for the first time in the history of ocean crises, entirely up to us. Let us go deeper into the physics of what happens to an ocean when it loses oxygen, because the cascade of consequences extends far beyond the obvious fact that fish cannot breathe in water without dissolved oxygen. The oxygen content of seawater is connected to virtually every other chemical property of the ocean, and when oxygen declines, A domino sequence of chemical changes follows that transforms the ocean into a fundamentally different environment. In oxygenated water, iron exists in the oxidized ferric form, iron in the +3 oxidation state, which is largely insoluble and therefore unavailable to phytoplankton. In anoxic water, iron is reduced to the ferrous form, iron in the +2 oxidation state, which is soluble and biologically available. When deep, anoxic water upwells to the surface, as it does along the Pacific coast of North America and in other coastal upwelling systems, it carries this dissolved ferrous iron with it. Iron is a key limiting nutrient for phytoplankton in many parts of the ocean, and the supply of iron from upwelling anoxic deep water can trigger intense phytoplankton blooms. These blooms produce organic matter that sinks, decomposes, consumes oxygen, and deepens the anoxia in the deep water from which the iron came. The feedback is self-reinforcing. Anoxia releases iron. Iron drives biological productivity. Productivity drives decomposition. Decomposition drives anoxia. This iron-oxygen feedback was almost certainly operating during the oceanic anoxic events of the geological past, and it helps explain why OAE2 persisted for hundreds of thousands of years. Once established, the anoxic state is self-sustaining through multiple feedback loops. The iron feedback is one. The nitrogen feedback is another. Denitrification in anoxic water converts nitrate to nitrogen gas, removing a key nutrient from the biologically available pool and reducing productivity, but simultaneously producing nitrous oxide, a greenhouse gas that contributes to warming, which reduces oxygen solubility. The phosphorus cycle provides a third feedback. In oxygenated sediment, phosphorus is bound to iron compounds and buried, removing it from the water column. In anoxic sediment, when those iron compounds are reduced, the bound phosphorus is released back into the water, fueling additional biological productivity and additional oxygen consumption. The anoxic ocean is a different chemical machine from the oxygenated ocean, and once established, it tends to stay in the anoxic state. The stability of anoxic states in the ocean is one of the reasons that OAS lasted so long in the geological record. It is also one of the reasons that concern about modern ocean deoxygenation should not be dismissed on the grounds that the ocean has recovered from previous OAEs. Yes, the ocean recovered, eventually, but the timescales involved were hundreds of thousands to millions of years. And the biosphere that existed before OAI2 was substantially different from the biosphere that existed after it, because the extinction of vulnerable species and the restructuring of ocean food webs that occurred during the event were not reversed. The ocean that recovered was a different ocean, populated by different assemblages of organisms than those that existed before. Recovery is not restoration. The comparison with modern dead zones in terms of the stability of the anoxic state is illuminating. The annual dead zone that appears every summer in the northern Gulf of Mexico is not a permanent anoxic state. It forms in summer when thermal stratification is strongest and dissipates in fall when storms mix the water column and cooler temperatures reduce stratification. This seasonal reversal is what makes it a recoverable problem in principle. But several features of the modern situation suggest that the seasonal recovery may not be guaranteed indefinitely. First, the nutrient loading that drives the Gulf dead zone has not been consistently reduced over recent decades, despite decades of policy attention. The size of the dead zone continues to vary primarily with weather conditions. Wet years bring more nitrogen runoff and produce larger zones. Dry years produce smaller ones. But the underlying nitrogen delivery has not shown the sustained decline that would be needed to meaningfully reduce the average zone size. The agricultural system of the Mississippi Basin is not becoming less nutrient-intensive over time. Second, the warming of the Gulf of Mexico has strengthened the thermal stratification that prevents reoxygenation of the hypoxic layer. Warmer surface water means a stronger density barrier between the warm surface layer and the cooler, oxygen-depleted deeper water. As the Gulf warms in response to the broader warming of the ocean, the seasonal dead zone becomes harder to ventilate. The fall mixing that normally breaks down the stratification becomes less effective, because the temperature difference between surface and deep water that it needs to overcome is larger. Third, and most importantly, the interannual variability in dead zone size masks a long-term trend that is unfavorable. The year-to-year variation in size is large, driven primarily by the amount of spring rainfall and the timing of stratification, which makes it easy to point to years with smaller than average dead zones as evidence that the problem is manageable. But the multi-decadal trend in the size of the dead zone is unmistakably upward, tracking the increase in nitrogen delivery from the increasingly fertilized agricultural heartland. The sulfur chemistry of anoxic water deserves mention because it is both scientifically important and viscerally dramatic. In anoxic water, the bacteria that use sulfate as an electron acceptor produce hydrogen sulfide as a byproduct. Hydrogen sulfide, the compound responsible for the smell of rotten eggs, is toxic to virtually all aerobic life, at concentrations far lower than those that exist in strongly anoxic water. In the Black Sea, below the chemocline, hydrogen sulfide concentrations are high enough to kill any aerobic organism almost instantly. The boundary between the oxygenated and anoxic layer in the Black Sea is not merely a chemical boundary, it is a survival boundary. Above it, life as we normally understand it. Below it, death. This hydrogen sulfide chemistry played a central role in the end-Permian extinction. As the ocean became globally anoxic at the end of the Permian, hydrogen sulfide accumulated in the deep water to concentrations that had no modern parallel outside extreme environments like the Black Sea. Eventually, researchers have proposed the hydrogen sulfide-laden deep water shoal upwelled into shallow environments, carrying its toxic cargo with it. The chemical evidence in end-Permian marine sediments includes distinctive sulfur isotope signatures, consistent with hydrogen sulfide reaching the ocean surface in some regions. The hydrogen sulfide may also have been released into the atmosphere, where it would have been toxic to terrestrial organisms, and where its reaction with ozone would have further depleted the ozone layer, exposing both marine and terrestrial life to elevated ultraviolet radiation. The end-Permian anoxia was not merely a deep ocean phenomenon. It was a global chemical catastrophe that touched every environment from the deep sea floor to the terrestrial surface. Modern dead zones do not produce hydrogen sulfide at concentrations approaching those of the end-Permian ocean. But the chemistry is the same kind of chemistry. In the most severely anoxic bottom water of modern dead zones, hydrogen sulfide is detectable, and its concentrations can reach levels toxic to benthic organisms, the animals that live on and in the seafloor. The black sediment of the anoxic Baltic is colored by iron sulfides produced by the same bacterial metabolism that generated hydrogen sulfide in the end-Permian ocean. The difference is scale, not chemistry. One of the more counterintuitive aspects of ocean deoxygenation is its relationship to biological productivity. You might expect that a less oxygenated ocean would be a less productive one. Less oxygen for organisms to use, less energy available for biological processes. But in the short term, the relationship runs the other way. Dead zones form because biological productivity was high, because phytoplankton bloomed in response to nutrient inputs, producing so much organic matter that its decomposition overwhelmed the oxygen supply. The most biologically productive periods of Earth's history, measured by the accumulation of organic-rich sediment, are often also the periods of greatest anoxia. The black shales that mark oceanic anoxic events are organic-rich precisely because the high biological productivity of the surface ocean produced organic matter faster than it could be decomposed in the well-oxygenated waters below. This means that the transition from oxygenated to anoxic ocean conditions can involve a period of high biological productivity at the surface, even as the deep water dies. The surface blooms and the deep suffocates simultaneously. Modern dead zones show this pattern. The surface water over a dead zone is often highly productive, green with phytoplankton, while the bottom water is anoxic and lifeless. The surface abundance masks the bottom catastrophe, and the biological signal from satellite ocean color measurements, which see only the surface, may actually be misleading about the ecological health of the water column below. In the geological record, this same pattern appears during OAS. High surface productivity, low bottom oxygen, accumulation of organic matter in the sediment. The black shales that record ORS are among the most carbon-rich rocks in the geological record, preserving organic matter that accumulated when the deep ocean was too anoxic to decompose it. These black shales are, in economic terms, the source rocks for many of the world's petroleum reserves. The dead zones of the geological past converted to oil over millions of years by the heat and pressure of burial. There is a certain geological irony in the fact that we are burning petroleum derived from the organic matter that accumulated during ancient ocean anoxia events, thereby releasing the carbon stored during those events back into the atmosphere, where it is warming the climate and driving modern ocean deoxygenation. The monitoring infrastructure for ocean oxygen is inadequate to the scale of the problem. The ocean is vast. 339 million square miles of surface, with an average depth of 2.3 miles. And direct oxygen measurements require either research vessels or autonomous instruments, both of which are expensive and limited in geographic coverage. The Argo Float program, which maintains a global array of approximately 4,000 autonomous floats that measure temperature, salinity, and oxygen throughout the water column, has dramatically improved our monitoring capabilities. But 4,000 floats in 339 million square miles of ocean represents one float per approximately 85,000 square miles. A sampling density that cannot resolve the fine-scale structure of oxygen minimum zones or the specific locations of developing hypoxia. Our knowledge of the current state of ocean oxygen is derived from a monitoring system that is vastly undersampled relative to the complexity of the system it is trying to observe. This monitoring gap matters because early warning of expanding dead zones and oxygen minimum zones requires dense, real-time data that we do not have. We often discover dead zones and hypoxic events after the fact, when fish kills are reported or trawl surveys come up empty. The lag between the development of hypoxic conditions and their detection means that ecological damage is often already extensive before interventions can be designed or implemented. Improving the monitoring infrastructure, more Argo floats, more autonomous underwater vehicles, more coastal sensor networks, is both technically feasible and economically modest relative to the economic value of the fisheries and coastal ecosystems that the monitoring would help protect. The interaction between ocean deoxygenation and acidification is another dimension that deserves attention. Ocean acidification, the reduction in seawater pH caused by the absorption of atmospheric carbon dioxide, affects the ocean through different mechanisms than deoxygenation, but often operates in the same geographic areas and affects many of the same organisms. Acidification reduces the ability of marine organisms to build calcium carbonate shells, the material that makes up the shells of oysters, clams, corals, and many plankton, by reducing the availability of carbonate ions in the water. In combination with hypoxia, acidification creates what researchers have called multiple stresses or compound stresses, conditions in which organisms face several simultaneous physiological challenges, each manageable separately but potentially lethal in combination. The Eastern Pacific upwelling system that is experiencing expanding hypoxia is also experiencing significant acidification, because the same upwelled water that is low in oxygen is also enriched in carbon dioxide from the respiration of deep-sea organisms and the absorption of anthropogenic carbon dioxide. Oyster larvae in Pacific coast hatcheries have experienced significant mortality events, attributed to the corrosive chemistry of the upwelled water, leading some hatchery operators to monitor seawater chemistry in real time and adjust their operations accordingly. This is an example of an industry adapting to the changing ocean chemistry, adaptive management in response to compound stresses, but it is also a demonstration of how rapidly the conditions in these waters are changing. The combination of deoxygenation, acidification, and warming, the three major chemical and physical stresses associated with climate change and eutrophication, creates an ocean that is increasingly inhospitable to the organisms that have evolved in its previous, more stable state. The paleontological record of previous marine extinctions suggests that it is precisely this combination of stresses operating simultaneously that is most effective at driving widespread biodiversity loss. Single stressors are survivable by species with sufficient physiological plasticity. Multiple simultaneous stressors reduce the available refugia and the range of effective adaptive responses. What will the ocean look like in 50 years if current trends continue? The honest answer is that we do not know with precision, because the interactions between the multiple stresses and the complex ecology of marine systems are not fully predictable. What the models project, and what the geological record suggests, is a systematic expansion of low oxygen conditions, more dead zones, larger dead zones, more widespread oxygen minimum zones, deeper encroachment of hypoxia into the coastal zones where the most productive fisheries operate. The most vulnerable ecosystems are the same ones that are most important economically and biologically. The shallow coastal upwelling systems, the tropical coral reef systems, the productive continental shelf fisheries. These are the systems that will be most affected first. The historical moment we are in has no geological analogy. The closest analog is the beginning of an oceanic anoxic event, but at a rate of change that is orders of magnitude faster. The closest biological analog is the beginning of a mass extinction event, but with the unique feature that the organisms causing the change, us, are capable of understanding what they are doing and of changing course. This is not a comfortable position to occupy, but it is the actual position, and the geological record is quite clear about what happens in its absence. The dead zone that forms every summer in the major ocean, visible from satellites as a region of anomalously high biological productivity and anomalously low oxygen in the bottom water, is a warning. Not because it is new, it has been there for decades. Not because it is unique, there are 500 like it, but because of what it represents, the visible surface expression of a process that has, in the geological record, been associated exclusively with catastrophic outcomes when allowed to proceed to its natural endpoint. The ocean is not yet globally anoxic. The oxygen minimum zones have not yet reached the surface across entire ocean basins. The chemistry that kills the deep is not yet killing the shallow in most of the world. We are at the beginning of this process, not at its endpoint. But the geological record is unambiguous about where the beginning leads if the drivers are not addressed. Every organism in every dead zone, every crab that fled to shore, every fish that suffocated in hypoxic water, every square mile of anoxic Baltic seafloor covered in sulfur bacteria. All of this is data. Real-time data about a process that the geological record has already run to completion several times, with outcomes that we can read in black shales and mass extinction boundaries, and the changed fossil assemblages that mark the aftermath of ancient ocean crises. We have the data, we have the geological record, we have the scientific understanding, we have, in principle, the technological and policy tools to change the trajectory. The question is not whether we know what to do. The question is whether we will act at the scale and the speed that the geological precedent suggests is necessary. The dead zones are the ocean's answer to that question. updated every summer, visible from space, measured by instruments, documented by researchers, and expanding despite decades of awareness that they exist and harm. What we do with that knowledge is the choice that defines this moment in the history of the ocean, and in the history of the species that is, for the first time, capable of making it deliberately. There is a dimension of the ocean oxygen story that rarely surfaces in scientific or policy discussions, but that I think is essential for understanding the full weight of what we are dealing with: the relationship between ocean deoxygenation and the deep evolutionary history of life. The oxygen content of the ocean has not always been what it is today. The early ocean, the Archean ocean of 3 to 4 billion years ago, was essentially anoxic throughout. The Great Oxidation Event of 2.4 billion years ago began the process of oxygenating first the atmosphere and then progressively the ocean. But the oxygenation of the deep ocean was a slow and geologically recent process. The deep ocean did not become fully oxygenated until the late Precambrian, perhaps 600 million years ago, and it was only after that oxygenation that the complex multicellular animal life we associate with the fossil record became possible. The evolutionary history of animal life is therefore a history of organisms that evolved in an oxygenated ocean and are dependent on that oxygenation in fundamental ways. The physiological machinery of animal respiration. The hemoglobin that carries oxygen in vertebrate blood, the hemocyanin that does the same job in crustaceans and mollusks. The gill structures that extract dissolved oxygen from water is ancient, conserved across hundreds of millions of years of animal evolution and exquisitely calibrated to the oxygen concentrations of the modern, well-ventilated ocean. These systems were not evolved to tolerate extended hypoxia. They were evolved to exploit abundant oxygen. When ocean oxygen declines, these organisms face a physiological challenge that their evolutionary history has not prepared them for in the modern context. Some species have some tolerance. They can reduce their metabolic rate, shift to anaerobic metabolism temporarily, or behaviorally avoid low oxygen areas. But the tolerance is limited, and for many species, particularly those with high metabolic rates like tuna and billfish, the tolerance is very limited. The expanding oxygen minimum zones and multiplying dead zones represent a contraction of the habitable volume of the ocean for the organisms that evolved in it. The ecological consequences extend well beyond the direct physiological stress. The restructuring of marine communities in response to expanding hypoxia changes the distribution of predators and prey in ways that cascade through food webs. When high-oxygen surface fish are compressed into a shallower surface layer by the expanding oxygen minimum zone below, they become more vulnerable to predation by seabirds and marine mammals that hunt at the surface. The prey species they depend on may not be similarly compressed, creating a mismatch between predator and prey distributions. The entire three-dimensional ecology of the water column is reorganized by the oxygen landscape, and the reorganization benefits organisms tolerant of low oxygen: jellyfish, certain species of squid, some bacteria, at the expense of the large, active, metabolically demanding fish that form the backbone of marine fisheries. The proliferation of jellyfish in low-oxygen environments is a documented phenomenon with implications for marine ecosystem structure. Jellyfish can tolerate much lower dissolved oxygen concentrations than most fish. They have simple body plans and low metabolic rates that make them relatively efficient oxygen users. In environments where fish are excluded by hypoxia, jellyfish can thrive, consuming zooplankton and smaller organisms without the competition from fish that would normally regulate their populations. Some bays and coastal embayments that were previously productive fish habitat have shifted to jellyfish-dominated systems under the influence of persistent hypoxia and eutrophication. A regime shift that is difficult to reverse because the jellyfish themselves contribute to the conditions that sustain their dominance by consuming the zooplankton that would otherwise graze the phytoplankton blooms that drive eutrophication. The regime shift concept is important in this context because it points to one of the most concerning aspects of the modern dead zone situation: the non-linearity of ecological responses to environmental change. Ecosystems do not always degrade gradually and reversibly. They sometimes shift abruptly from one state to another, a shift that may be triggered by a gradual change in conditions crossing a threshold. And once shifted, they resist returning to the previous state, even if the conditions that triggered the shift are partially reversed. The Baltic Sea shows elements of this kind of regime shift. Decades of nutrient reduction efforts have achieved some improvement, but the sea has not returned to the less eutrophic state of the mid-20th century, in part because the internal nutrient cycling of the sediment sustains eutrophication even when external inputs are reduced. The Chesapeake Bay offers another instructive example. The bay has been the subject of sustained and seriously funded restoration efforts for more than 30 years, with significant reductions in nutrient inputs from both point sources like sewage treatment plants and non-point sources like agricultural runoff. Some indicators have improved. Certain grass beds that oxygenate shallow water through photosynthesis have recovered in some areas. Some subpopulations of oysters, which are themselves important oxygen regulators through their filter feeding, have shown recovery. But the bay's dead zone, the hypoxic layer that forms in its deep channel every summer, has not disappeared. It has, in some metrics, improved modestly. But the system has not returned to the less hypoxic state of the early 20th century, because the watershed delivering nutrients to the bay continues to be farmed intensively, because the climate warming that strengthens stratification continues, and because the legacy nutrients stored in the bay sediments continue to fuel productivity even without external input. The lesson from the Chesapeake is that the timescales of ecosystem recovery are long, longer than the political cycles that fund restoration programs, longer than the careers of the scientists who design them, longer than the patience of the stakeholders who depend on the bay's fisheries for their livelihoods. This timescale mismatch between ecological reality and human institutional capacity is one of the deepest challenges in addressing the dead zone problem, and it has no easy solution. The global ocean oxygen budget is tracked by an international network of researchers using a combination of ship-based measurements, autonomous platforms, and satellite observations synthesized into global analyses that are updated periodically. The most comprehensive recent assessment, published by an international team drawing on decades of data, documented a global loss of dissolved oxygen from the ocean of approximately 2% between 1960 and 2010. A loss of approximately 77 billion metric tons of oxygen from the ocean over 50 years. This is a number that is difficult to make intuitive, but its significance is in the trend and the distribution rather than the absolute quantity. The 2% average loss conceals much larger losses in specific regions and at specific depths where oxygen minimum zones have expanded most dramatically. The trends in ocean oxygen are not uniform, and they are not all bad. Some high-latitude regions have shown oxygen increases in recent decades, as ocean warming has changed the balance between stratification and mixing in complex ways. The polar oceans are among the most vigorously ventilated in the world. They are the primary sites of deep water formation, where cold, dense, oxygen-rich surface water sinks and circulates through the deep ocean. As the polar regions warm, the dynamics of deep water formation change in ways that are not uniformly negative for oxygenation, though the net global trend remains one of oxygen loss. The most direct and most alarming trend is the shoaling of the oxygen minimum zones, their expansion upward toward the surface in the tropical and subtropical Pacific, Indian, and Atlantic Oceans. In the eastern tropical Pacific, the upper boundary of the oxygen minimum zone has risen by tens of meters over recent decades in some regions, reducing the oxygenated surface layer available to fish and other aerobic organisms. In the Arabian Sea, one of the most intense oxygen minimum zones in the world, the zone has expanded and intensified measurably. These changes are not subtle. They are detectable in standard oceanographic surveys, and they represent a real and significant reduction in the habitable volume of the ocean. The connection between ocean deoxygenation and human food security is more direct than it might appear from an ecological perspective. Approximately 3 billion people worldwide obtain a significant portion of their dietary protein from seafood. Marine fisheries provide livelihoods for hundreds of millions of people, particularly in developing countries where alternative protein sources are limited or expensive. The fish species that are most economically important, the tuna, the cod, the herring, the anchovy, the squid, are precisely the oxygen-sensitive, high-metabolism organisms that are most vulnerable to expanding oxygen minimum zones and increasing hypoxia. The compression of these fish populations into shrinking oxygenated habitat creates a perverse dynamic. Catches may actually remain stable or even increase in the short term as the fish concentrate in accessible surface waters, masking the underlying decline in total population and habitat quality. This dynamic, the deceptive stability of near-term catch statistics as ecosystems degrade, has been seen repeatedly in the history of fisheries management, where declining populations were not recognized until the collapse was already underway. The monitoring of oxygen conditions in the water column, not just the tracking of fish catches at the surface, is essential for detecting the early warning signs of the kind of population collapse that expanded hypoxia can trigger. The political economy of addressing ocean deoxygenation is deeply challenging. The coastal dead zones, which are the most visible and politically tractable part of the problem, require changes in agricultural practice across entire river basins. Changes that affect the economic interests of millions of farmers, the industries that supply fertilizers, and the political systems that subsidize intensive agriculture. The open ocean deoxygenation, which is the deeper and ultimately more serious part of the problem, requires addressing climate change, a challenge that involves the interests of every fossil fuel-producing nation, every industrial economy, and every consumer of energy in the world. Neither challenge is politically simple, and neither will be addressed by good intentions alone. What is needed is a combination of targeted interventions and systemic change. On the targeted side, precision agriculture to reduce nutrient overuse, wetland restoration to filter nutrients before they reach the coast, improved wastewater treatment in coastal cities, monitoring systems that provide real-time data on oxygen conditions in key marine areas. On the systemic side, the reduction of greenhouse gas emissions that is driving the warming causing open ocean deoxygenation, and the recognition in international policy frameworks that ocean oxygen depletion is a first-order global environmental threat, deserving the same level of attention and resource mobilization as climate change, of which it is, in fact, an integral component. The fact that these solutions are known and technically feasible does not make them politically easy. But the geological record provides a useful framing for the political challenge. The geological record shows that the relevant comparison for the modern dead zone expansion is not previous episodes of localized coastal hypoxia from which recovery occurred. The relevant comparison is the Oceanic Anoxic Events and the end-Permian extinction, events that involved global-scale deoxygenation and produced catastrophic biodiversity loss. From this perspective, the question is not whether we can afford the cost of reducing nitrogen pollution and greenhouse gas emissions. The question is whether we can afford not to. The standard framing of dead zones as a water quality problem addresses the coastal symptom. It does not address the deeper cause, the warming climate that is expanding oxygen minimum zones globally. And the deeper cause is the one that connects our present situation to the geological record of catastrophic anoxia. The coastal dead zones and the open ocean deoxygenation are not two separate problems. They are two expressions of the same process, operating at different scales and different speeds. The geological record is not a prediction. It is a record of what has actually happened when ocean deoxygenation has proceeded, without the intervention of any force capable of arresting it. In the geological past, there was no such force. The ocean did what the chemistry compelled it to do, and the biosphere experienced the consequences. For the first time in the history of ocean crises, a species exists that understands the chemistry, reads the geological record, monitors the present conditions, and has the technical capacity to intervene. That species is us. The question is not capability, it is choice. Every summer, more than 500 dead zones form across the world's oceans. Every decade, the oxygen minimum zones expand measurably. Every year, the global ocean is slightly less oxygenated than it was the year before. And every day, the atmospheric carbon dioxide that is driving the warming, that is driving the open ocean deoxygenation, increases by another fraction of a part per million. The ocean does not make choices. It follows chemistry. The chemistry is following the carbon dioxide. The carbon dioxide is following the choices we make. Whether we achieve that different outcome depends on what we do with the knowledge we have. The dead zones are telling us every summer that we have not yet done enough.